Hello everyone, I hope I am audible. So I will start the session after 6. I am sharing my screen. Please let me know in the chat box if you can see it.
Yes, ma'am.
Okay,
Good evening.
good evening. Thank you. Thank you for the confirmation. Let's wait for a couple of minutes. I'll start the session once
Mm-hmm.
people join. Okay. Okay, so one minute. Okay, hello everyone. I hope I'm audible. So it's already 6, so let's start the session. Uh, I'm a bit sick today. I Please bear with me. If you can't hear me properly, then let me know. I will try to speak louder. So let me give a brief introduction about myself first. I am Ananya. I am a PhD scholar in the Department of Electrical Engineering in IIT Kanpur. My specialization is microelectronics and VLSI, and I am working in semiconductor devices lab in electrical engineering department here. So I will be your TA for the session, and if you have attended the last session, so some of you may not have attended the last session, so let me first briefly talk about these live sessions. So I think many of you have done NPTEL courses earlier. So in NPTEL courses, typically you will have a live session for each course, and these live sessions are for problem. These are like problem solving session, like tutorial session. In this course, we don't have like that many numerical question or coding problems, but we will see similar question. We'll try to solve similar questions, like you get those questions in assignments. So these are mainly tutorial session. I will give a brief overview of the topics those were covered in this week. Like for this session, this will be week 2. But don't expect it. I will talk about everything. I try to give a brief overview so that everyone is on the same page. So ideally, you should watch all the videos before coming to this session. Okay. Okay, I hope my screen is also visible. So this course is sensors and actuators. So in this course we talk about sensors and actuators, their design, the like basic working mechanism as well as their fabrication, but is also very important. And today, like in this week 2, most of the lectures were on fabrication of these sensors. So let's start the session with a brief overview of the topics those were covered in this week. Let me first check how many people are there. Okay. Also, I want to mention that I'm recording the session. This is just for your information, but feel free to ask any doubt. You can unmute yourself and or write in the chat box. For most of the time for the session, I will be in the presentation mode, so I will not be able to check the chat box, but I will check your questions if you write in the chat box periodically, like in between each questions and probably each slide. Okay. Yeah, so unmute yourself if you feel, please feel free to talk or discuss anything in between, because I will not be able to see your questions right away if you write in the chat box. Okay. So in this week, in first few lectures, we discussed about VOC sensor. So what is VOC? VOC stands for volatile organic compound. Okay, so can you give a few examples of volatile organic compounds? Few examples. What are some volatile organic compounds? Okay, I'm not getting any response. So few examples of volatile organic compounds are acetone, can be methanol, ethanol, okay, and there are a few others you can just check. Okay, these are few examples of VOCs. Now why we want to sense VOCs? First of all, where we can find these volatile organic compounds. Okay, so in paint, okay, this is one example that was given in the class, so I'm also giving it. And in this course I mostly talk about VOC is present in a human breath. Okay, human breath contains certain amount of VOCs of different concentration, and based on the analysis of these VOCs, we can get some information about the person, some information about the health of the person. One example that was given in the class, that a diabetic person will have a different concentration of acetone in his or her breath compared to a non-diabetic person. Okay, so some of you are maybe working in this area, so you'll know it better. And another example is that we this is also used for detection of like if someone if a person is drunk, then also it is used to detect death. This is mainly for drink and drive cases, so this VOC sensors are used. For health monitoring, it is mostly for these are used as a human breath sensor that based on the concentration on different types of this VOCs. Okay. Now, why it is important to have sensors, VOC sensors for human breath analysis? Because it is a non-invasive way of health monitoring and disease detection. Okay. uh, Non-invasive. I hope that you can clearly see my can understand my handwriting. Okay, it's not very good. I think you get the point. So what is non-invasive method of health monitoring? So there are a few methods which are invasive. For example, if you are making a sensor that is based on that requires a blood sample, then you need to take a blood sample out from a person, so that will be like an invasive method. And we normally prefer non-invasive methods like which are based on say human breath or can be other things. So this is very simple, as well as it is a non-invasive method which is always preferable. Like if you can uh, get information without taking out say blood, or without basically torturing the person, because these sensors are for health monitoring, so the person may be already weak, or like it can complicate their health situation. So non-invasive methods are always preferable, and that is why human breath sensor are mostly useful in that way. And you should also remember that these sensors, if these are used for health monitoring or biomedical purposes, so this has to be like very accurate and very precise. Okay, you should be able to tell what is the condition of the person, not just in a qualitative way, say that this person is diabetic or not just that way, like how what is the condition of the person, how critical is the condition of the person, that also you should be able to tell. So this sensors has to be very accurate. So in general, not a single sensor is used, many sensors are used, array of sensors are used, and these are combined, and then a system is made from those sensors so that it can accurately detect the condition of the person. Okay. And one more thing, that is VOC sensors can be this can be like targeted, those can be selective. For example, it's a sensor can be selective towards a certain VOC. So if you want to detect multiple volatile organic compounds, then you have to use an array of sensors. Okay. Next in the course, next in the class, briefly e-nose was discussed. So what is e-nose? E-nose means electronic nose. So sorry for the background noise. Okay. So what is electronic nose? So our nose is a sensor, right? It's a very complex sensor. It can detect smell, and then it sends the output, the sensing output, to our brain, and our brain is like the processing unit. Our brain is the processing unit. It takes this information of the sensor, and so sorry. Can you hear me properly? I'm so sorry for the background noise, but for some reason, if I use a headphone, then I don't get the recording clearly. So that is why I'm not using an earphone. Please confirm if you can hear me.
Yes, ma'am, it's okay.
It's
I
okay?
can.
Okay,
Yeah.
thank you. Okay. Okay, so we are discussing about e-nose, electronic nose. So our nose is a sensor. It's a very complex sensor, right? We remember different types of smell. How we remember it? We smell it, which is like using like our nose is the sensor. It provides that information to brain, and our brain is the neural network. It remembers all the information like since from birth, and then it uses that information. So that is why we recognize different smells, because our brain remembers everything. So okay, so people try to mimic this kind of system electronically. Okay, so that is what e-nose is. So in e-nose there will be different types of sensor for different types of gas detection. So and the information of the sensor, the output of the sensor will be connected to some signal processing unit that will have a microcontroller or like a system. Okay, it can be a microcontroller or it can be like a big system that can do the signal processing of different types of the output of the sensors. Okay, and based on that, uh, like our brain can remember different information, the system, the signal processing unit, there will be a certain memory unit also. That unit will remember this information, and later when it is used, based on that information and based on the previous memory, it will give some output, and based on that something will be done. Okay, I can give you one example. One of my teachers, he used to work in enos. So those systems were used for in tea industries. Okay, so based on the smell of tea leaves, the quality of the tea can be detected. Usually what like normally a person will test it, a person will smell it, and person will do this job. Then he tried to kind of mimic that system electronically, so that uh, uh, like when if a tea leaves are provided, then the system will tell whether the quality of the tea leaves are good or not. So in that way, there may be other application also. Like many of these sensor systems are inspired from nature, inspired from human body. So e-nose is one example. So I will write it down. I hope that you got the idea, like why people try to make electronic nose or e-nose to simplify different types of work. That I give you an example. That is not for health monitoring or biomedical purposes, but for health monitoring and biomedical purposes also, this kind of systems can be used. Okay, so just I'll make few notes. Okay. So our brain is the neural network, so we try to mimic, like nowadays this artificial network and deep learning, all these concepts are inspired from our brain. Our brain can process a lot of information, remember a lot of things. Okay, we try to mimic it with electronic system. Okay, so if you are interested, you can look about, like you can just do a Google search on enos, and you'll get different articles that will explain different uses of this kind of a system. Okay, now many of these VOC sensors are MOS based. Okay, So what is MOS here? Metal oxide semiconductor. It is not the like MOSFET, that MOS. So what are metal oxide semiconductors? Some of the examples are ZNO, SNO2, and there are other examples also you can look. So many of these VOC sensors are MOS based. So this material is used as a sensing layer in this kind of sensors. I encourage you to look for a sensor dataset for a VOC sensor. You can just like find it in Google. That there are many VOC sensors available in market. Those are commercially available. You can find the data sheet, and many of these are MOS based. You can check what is the metal oxide semiconductor conductor that is being used in the sensor, and then like because these most of the sensors are MOS based, they normally operate at higher temperature, so that this material actually acts as a sensing material. So if you have a MOS based VOC sensor that operates at a higher temperature, not at room temperature, then you will also need a microheater along with the sensing elements. So for this kind of sensor, what you need a sensing material, which will be metal oxide semiconductor, sensing material, plus electrode, because ultimately you will measure the resistance of this material and the change in resistance of this material due to different concentration of volatile organic compounds. So you need a sensing material, a sensing layer, which will be like a film, and then electrode. Okay, and then to power this kind of like power of the sensor, we will need a microheater. Okay, now how a microheater is integrated with the sensor, that was discussed in the class in this week also, in previous week also. So how you do, you first make the microheater, on top of it you deposit an insulating layer, so that the heater is not in direct contact with your electrode or your sensing layer. It does not interfere the sensing performance. That there will be an insulating layer, and on top of that you will make your sensor, which will be like a sensing material plus electrode, and you will measure the resistance or voltage, like depending on your configuration, how you design the sensor, you will measure the resistance or the voltage across the sensing material using the electrode configuration. Okay, so these were briefly discussed in one of the session, then few one of the class, and then it was also discussed in the class about the flexible sensors. Flexible sensors are used in health monitoring. People can wear it, that is why these are flexible sensors. So for example, you can wear like a watch. Okay, you can wear this array of sensor as a watch, and it can be connected to connected with a different system. Say it can be connected to a mobile or a desktop for health monitoring purpose. Okay, now one thing you should remember, that most of the sensors those were discussed in the class will be of silicon based. The substrates that is used in the sensors will be silicon, because the silicon based fabrication techniques are well known, so well established, so that is why we mostly use silicon. But for flexible sensors, silicon cannot be used. It's not a flexible substrate, so there are alternative substrates those were used. Based on that, the fabrication process can be a little bit different. Now there are few things you should also remember, that many of the flexible substrates, for example PDMS, those will not sustain very high temperature. So that is why the fabrication process or the sensor design should be in such that you don't want to operate the sensor at a very high temperature. You don't want to do like some deposition technique that will be like a very high temperature, because the substrate will not sustain that temperature. Okay, now this is like a trade-off that if you want a flexible sensor, then most of the time those are like does not go to very high temperature. Okay. Next, because this course is on sensors and actuators, so a few examples of the actuators were also discussed. So what is an actuator? It converts some energy into motion. So energy to motion, basically actuators are responsible for some movement uh, of the device or the parts of the device. Okay. Now, in this course, we mostly discuss about sensors in micrometer and nanometer range. So, most common types of MEMS actuators, those are of these types: piezoelectric, thermal, or magnetic. Okay, there are other kind of actuators also, but these were the example those were given in the class. So you already know what is piezoelectric effect, how piezoelectricity is like arises in a crystal, that I discussed in the last session also. You can go back and check. What happens in case of thermal actuator? It uses the thermal expansion for actuations. Okay, thermal actuators uses thermal expansion for actuations. Okay, because of at elevated temperature, at high temperature, normally different material changes its size and shape, and based on that some movement of some part in the system can happen, and that is what thermal actuations. Okay. Now what is magnetic actuators? So it magnetic actuators uses magnetic energy for movement, like for some movement. Okay. So there can be some magnetic components that you can either attract or repel using a magnetic field. Okay. So one example is solenoid. This kind of magnetic actuators are used in MEMS based systems for mechanical movement. Okay. If you want, you can look for different examples of different kinds of actuators. Okay, I hope this slide is clear. I will take a pause, and if there is any question, you can ask. You can just unmute or write in the chat box. Okay.
Ma'am, am I audible?
Yeah, yeah.
Ma'am, suppose I want to work on ethanol, means sensing ethanol.
Hmm.
So in lab, what will be the procedure like VOC? How we'll prepare and how we'll get that particular ppm? Actually, I searched everywhere, but I am very confused about it.
If you want to control the flow, then you need a MFC. So that is for, like, that will give you the particular concentration. I'm not sure whether you will have the access to it or not, because these are these are usually expensive, but there are different types of MFCs also. You can search. I will write it here. You can just
Okay.
type it and check. Okay.
Okay, like ma'am, is there any formula or something like if my guide will ask me, so how will you calculate ppm. Suppose we are working on 200 ppm or something, then she'll ask me like how you're doing it and how you're calculating it. So is there any formula or something?
See, I cannot tell you like directly formula, but I remember that one like my MTech supervisor, he used to tell me that so from volume concentration we can just tell that like how, what is the concentration. So if you if you have like certain amount of ethanol in a particular volume, and if you wait sufficient amount of time that it like everything is in vapor phase, so not in liquid state, if it is everything is in vapor phase, and you know the volume, and then you know the concentration, uh, you can just search. But I know that there is a method for this kind of compounds. If these are in a like a closed volume, then you can see that this amount of ethanol is present in this cubic, like in centimeter cube also, like per centimeter cube, something like that. You can just check. I'm sure you will find something in the internet. It is not a way like directly it will not give you the ppm. You can just calculate it. I don't remember exactly like what it was. She told me once that we used to like wait for sufficient amount of time so that all the ethanol is in evaporated state, it's in like vapor state, and then based on the volume we calculate the concentration.
Okay, okay, ma'am. Thank you.
Okay. Okay, let me go to the next slide. So is there any question? How can we measure the selectivity of the sensor? Selectivity you always measure with respect to the analyte you want to sense, and the analytes you don't want to sense. Like if you are making a sensor that is for say carbon dioxide sensing, then you don't want it to sense other gases, right? So suppose you are making a resistive type sensor, so it measures the change in resistance due to different concentration of carbon dioxide, say, and you are just say you are taking 100 ppm of carbon dioxide, and what is the change in resistance for that. Now what will be the other gases? So you check for different other gases also, what is the change in resistance of the sensor for 100 ppm of different types of gases. Now if the change in resistance is very low compared to carbon dioxide, that is what you actually want to sense, then you can say that the selectivity of the sensor is good. Again, there is no like I don't think there is a particular like cutoff that if the change in resistance is say for carbon dioxide the change in resistance is say 50%, I'm just saying it randomly, but your change in resistance for a different gas is say 5% or 10%, and you can actually differentiate that okay, this is not carbon dioxide, it's a different gas, then I think it's okay. Okay, again there is like I don't think there is any standard. uh, just how selective your gas is, it depends on your requirement, and yeah, that's how you check the selectivity of a sensor. I hope I answered your question. Okay. Okay. So if you have any question, you can just write in the chat box. I will check in between. Let's go to this slide. Okay. So this week, mainly the fabrication, microfabrication of the sensors were discussed, and what are different microfabrication techniques. So you can see this diagram here. So different microfabrication technique is first deposition. So you want to make a thin layer of your sensing film, say, then you deposit it. Okay, then there are different types of deposition techniques to deposit a thin film. I will discuss it briefly in this week, and maybe in later weeks if required. And then suppose you deposited a film. It's a uniform film using some deposition techniques. Now you want to pattern it. Say you don't want your material in this area, say, so you want your material like this. Okay, or you want to make some metal electrodes like this over your sensing film, say. Then what you do patterning and etching. So what is patterning? It's like making a pattern. You can see this is uniform film, and there is some patterning in these two diagrams. Okay, how we can do a patterning? We normally use photolithography, and for making a sensor in micro dimensions, photolithography is very good. If it is a nano sensor, the dimension is very small, few nanometers, then we have to go for e-beam lithography for patterning. But in this course we will discuss about photolithography. I don't think e-beam lithography will be discussed. So for patterning we use photolithography. Okay, I'll discuss it again. Okay, photolithography, this is to make a pattern. And then etching, this is basically patterning and etching are used together to get some pattern. Okay, so what is etching? It is like selective removal of some parts of the material of a uniform film, say. Okay. And another is doping. Doping will not discuss today. Doping is used, so you already know that we dope silicon either to make it p-type or n-type. So this is also a part of microfabrication technique, but we will mostly discuss about deposition, patterning and etching. These are used to make different types of microsensors. Okay, now first let's discuss about deposition technique. Now what is deposition? It is the deposition of a thin film over a substrate. Okay, now over a substrate means that there may be some patterning before, there may be something else on the substrate also. Say you have a substrate first, then you already made a micro heater on top of it, and there is this insulating layer on top of it. Okay, now say you want to deposit your thin film over this like this. Okay, okay, this is, say, your sensing material. Okay, now how you can deposit a thin film of your material of choice? There are two ways. We can do a physical vapor deposition, which is a physical technique, and either we can go for a chemical deposition technique. Now so physical vapor deposition technique is PVD. I discussed about this in the last week also. So what are different types of PVDs? So PVDs basically we can categorize as evaporation and sputtering. Okay, so what is evaporation? We evaporate the material of our choice, and then that evaporated material will make a film on the substrate. Okay, so we change the state of the material which is in solid form. We melt it first and then we vaporize it. So first of all we have to provide a lot of energy so that it gets melt and it goes to its vapor phase. And once it goes to vapor phase, it will move towards the substrate. So generally in case of evaporation, thermal evaporation and e-beam evaporation, there will be a board. You will place your material here, you will provide energy, and this will become it will go to its molten state. Then the material will be evaporated and you will place a substrate here, and it will form like a thin film of this material on the substrate. Okay, this is evaporation. Now, this melting and evaporation you can do either by thermal evaporation or by EVM evaporation. So in thermal evaporation, if the generally used for metals, so if your material has a low melting point, then you can melt it easily. If you have to provide a lot of energy, then and it cannot pass current through your material, then you go for EVM evaporation. And using EVM evaporation, certain materials which are not easy to melt easily can be also evaporated. Okay, so these are just different types of energy provided to the material, but the basic mechanism or the physical principle is kind of similar, which is evaporation. Next, what is sputtering? Sputtering is the ejection of material. So you hit your target, which is your choice of material, with argon gas or other gas I discussed in the last week. And when this sputtering gas will hit the target, and resulting the result will be ejection of materials, ejection of atoms from the target, and that ejected material will be deposited on the substrate. Okay, so this is like a hitting and then ejecting. Okay, so normally what you do, all these techniques you perform inside a vacuum chamber, because you don't want to, any contamination to happen on your film. Also, so you can see here that these atoms, those were evaporated, it should directly go and sit on the substrate. So you don't want any collision. Like if there are, if the vacuum is not good, there are other particles, then the particles removed from evaporated from this will collide with this other particles, and it will move to a different direction. So you don't want that. That is why we normally do this kind of deposition inside a vacuum system. Okay, so a good like if the vacuum is good, then the deposition is also will be good, better. Excuse me. Next is chemical deposition techniques. Chemical deposition techniques can be there are different chemical deposition techniques. We will mainly discuss about CVD, chemical vapor deposition. ALD is atomic layer deposition. If you want, you can just check how ALD works. So what happens in CVD, it's a chemical deposition technique. So some kind of chemical reaction is happening. Now normally this chemical reactions to happen, some energy will be required. Okay, in a normal CVD system, how we provide this energy? By using by providing heat, like heat as the energy source. Okay, now based on the setup, the mechanism will be similar, but based on the CVD setup, it can be categorized into different types. Atmospheric pressure CVD, APCVD. So in this in here the energy will be provided like heat energy, but the whole reaction, whole deposition is done in atmospheric pressure. In low pressure CVD, we will do this deposition at a lower pressure. It will not be like as good vacuum as we use in this physical vapor deposition techniques, but it will be at a lower pressure, so that the uniformity of our film is good, so that there is no contamination. It will give us better film basically at low pressure. And PECVD, plasma enhanced CVD. So there are many classifications of CVD. You can check. I'm just giving you these three. There are others also. In PECVD, so the energy is provided through a plasma. So these are normally APCVD and LPCVD are high temperature processes. PECVD is relatively low temperature process. So if you have like a substrate or something that cannot sustain very high temperature, then I think PECVD will work. Okay, I'll not go into the details of it. I don't remember many of the details also, but I just want to give you an overview of what are the different CVT techniques available. Okay, I hope it's okay. Let's go to the next slide. Next, what was discussed? So photolithography was discussed briefly. Photolithography is a patterning technique. Okay, this I have taken from Google Images. This explain the different steps involved in the photolithography. So it's a multi-step process, and usually you have to optimize your condition like each and every stage so that you get desired result. So what you do in photolithography, you take a substrate. There may be already some deposition is already maybe done. Just substrate means it can be substrate plus some patterning plus some deposition. Okay, so what you first do, you clean the substrate. So there are different cleaning techniques, like there are cleaning methods. So it can be a basic solvent cleaning, like you clean it with acetone and IPA and DI water. It can be it can be a piranha cleaning. If you want to make a good device, then you always start with a clean substrate. Okay, now after cleaning, what you do, you apply photoresist on the substrate, on the clean substrate. How you do? Generally this is done by using a spin coater. Okay, I hope you are familiar with photolithography. So what you do, in the spin coater there will be a vacuum chuck. You will place your sample on top of it. You will drop your photoresist here, and it will rotate. Okay, it will rotate at a very high speed. Now based on the speed, you will get a certain thickness of photoresist on top of your substrate. Okay, so this is by using spin coater. If you don't use a spin coater, there are certain photoresist, I have not seen it, but there are certain photoresist available that just kind of like a laminated sheet. If you are making like a big sheet of like a big device, then it can be like a laminated sheet. You don't have to do a spin coat, because you will not be able to do a spin coat. Basically there are certain photoresist, but the basic principle is that we use a spin coater to make a uniform layer of photoresist. Now this will be in solvent form. There will be certain solvent. So what we do baking after photoresist deposition, so that that extra solvent is evaporated. Okay, now we have a uniform photoresist film on top of our substrate. Now what we do, we selectively expose the photoresist. You already know what a photoresist is. Photoresist is a chemical that changes its properties when light is incident on it. Okay, so this is a mask. Okay, so some portion of the mask will be dark and some portion will be bright. Okay, how so have if you have seen a mask earlier, so I will give you an example. So this will be like a glass, and there will be some dark areas which will be chromium. Okay, and some bright areas, so light will pass through these areas, and light will not be able to pass through this chromium areas. Okay, the dark areas. So you use an UV exposure. Now the photoresist, there are different types of UV exposures. The photoresist will change its property based on the wavelength of the light. Let's not go into the details, just remember that it uses UV exposure. And after the exposure, you can see here in this portion light was incident, right? In this portion light was incident, and light was not incident in this part of the photoresist. Okay, now what you do a process called development. You dip it in a certain developer solution. Okay, now based on the type of the photoresist, you will get a pattern of the photoresist on top of your substrate. So this is for positive photoresist. So if what a positive photoresist is, in case of a positive photoresist, the portion where light is incident, that will become soft, that will dissolve in the developer solution. So you can see here, this portion gets removed. Okay, so this portion becomes soft and this got removed, dissolved in the developer solution. If it is a negative photoresist, so negative photoresist become hard due to the exposure of light. So this portion will remain after development. This portion will go away in the developer solution. So you get these two pillars. Okay. Now normally what you do, say you are using this to deposit your electrodes. So what you can do is you do a metal deposition using some PVD or CVD technique. For metal deposition we normally use a physical vapor deposition technique. So you get a uniform like this kind of metal layer on top of your substrate plus photoresist. This is for negative photoresist. Now what you do a polishing. It can be a chemical or a physical polishing, so that you first make like a certain level. Say you remove this part, okay, using some polishing technique, physical or mechanical, or physical or chemical. After that what you do etching. So you selectively remove only the photoresist part, not the metal part. Okay, so finally you will get these metal pillars on top of your substrate. This is the pattern for positive photoresist and this is the pattern for negative photoresist. So this is the photolithography process. So you can see here etching is also part in this patterning technique. Okay, we normally use patterning and like photolithography and etching together. So what is etching? It is the process of removal of material from a substrate. It is basically selective removal of material. Here you can see that our etching technique also actually remove the photoresist and not the metal part. Okay, so that is why it is important that it is selective removal. Now there are different types of etching. We can do using it some chemical etchant, so that is known as wet etching, and dry etching is that we use physical technique. Physical we use ions. We heat our pattern substrate using some ions, and that will remove some part of the some portion of the substrate plus photoresist or metal layer. So this is known as dry etching. Normally dry etching is not very selective. It will remove everything like from top. And if you want to use chemical as well as basically this is for selectivity. Okay, wet etching is very selective. Because you are using certain chemicals, those chemicals will react with certain material and that will only get removed. So wet etching is selective. However, these are not directional, because I think you know this. So suppose you want to remove a material from this portion, say, so wet etching will result you this kind of a structure. Okay, because it removes portion from here also, right? These are not very directional, but if you use a dry etching technique, then it will be directional. Okay, now best of both will be, so this is directional. Now the best thing will be if you can combine these two, and that is what is done in reactive ion etching. So selectivity of wet etching and directionality of dry etching is combined in reactive ion etching, but this is relatively expensive. Okay, now next few things were discussed are clean room protocols. There were few lectures available in this week, so I hope that you have already gone through it. There is not much to discuss about it, so I'll mainly focus on the theory part. Okay, I hope this overview is clear. uh, if if you have any question, you can ask, or I will go to the questions. What is the use of this photolithography? Where we mainly use it? Photolithography is used for patterning. I just give you an example. So the example that was given in the slide, in this figure that I showed you, that is to make, say, metal electrodes. So suppose you have a sensing layer, and you will measure the resistance of that material, say due to some analyte, due to some chemical, some gas. You are, say you are designing a VOC sensor, you are detecting acetone, and you have a sensing layer, some material that can sense acetone. Now say due to different concentration of acetone, the resistance of the material will change. Now how you will measure the change in resistance? You will measure the change in resistance using like, you will first make some electrodes. Like there are many examples, those were given in the lecture videos also. You have seen how electrodes are made. So what kind, you have seen that there are different configuration of electrodes. Can be simple two metal lines also, it can be interdigitated electrodes like this. Okay, so how you make it? So you make it using photolithography. The steps those were shown in the figure, that is you, like something similar is done to make using to make interdigitated electrodes or metal electrodes. And you basically, so one example that was discussed in the class is micro heaters. So how you will make those patterns? You will make those patterns using photolithography. You will not you cannot selectively deposit, or you will not selectively like deposit and make a design of micro heater. You will either do uniform deposition and then pattern, or you will first do a patterning and then we will deposit and remove the layer, like that was discussed in this figure. Okay, basically to make different designs we use photolithography. Okay, and these are very important when we talk about micro and nano sensors, because in micro and nano sensors, don't think we'll be able to make nano dimensions in using photolithography, but for micro dimensions, for patterning in micro dimensions, we can easily use photolithography. And because we are discussing MEMS based system, micro sensors, that is why photolithography is very important. We are trying to make small devices like small sensors and actuators. How we will do it? We cannot manually do it. We use this kind of patterning and etching technique for that. Okay. I hope that you all have watched the lab videos. Okay, please like go through it if you have not. Clean room protocols were discussed. I think there are 3 videos. You can watch those. So like the last session, I will give you the question. Wait for a couple of minutes so that you can answer me in the chat box. Okay, and if not, then I will give you the answer. So the first question is, what are the most common type of energies used in remotely operated vehicles. Okay. What are the most common types of energies used in remotely operated vehicles? This was discussed in one of the lectures. If you have watched the videos, then we'll be able to answer it. Okay. I'll wait for a couple of minutes. I will wait till guys can write in the chat box. Okay. Since mostly the assignments are from the lecture videos, so I'm also trying to give you questions those were discussed in the lecture videos. Okay. I can give you a hint that there are three types of energies which are most common in ROVs. One, I should be able to answer very easily. You know about these automatic cars nowadays. Okay, what energy those cars use. Electric, hydraulic, and pneumatic energies is electricity or combination of electricity and hydraulic is. So you are right. What are the different types of energies which are used in ROVs? I will write down the answer. Electric current or electric energy, hydraulic pressure, and pneumatic pressure. Okay. Electric current is very common, like you already know about different like EVs. These are very common nowadays. Hydraulic pressure is what? Water pressure. So I tried to look like how it is used in case of RBs. So hydraulic pressure is used to, like, water pressure is used to move robotic arms in many vehicles. Okay. So you can search for those examples, those are available. Okay. And what is pneumatic pressure? Pneumatic pressure is like how you, what is this kind of energy where you use compressed air. So there will be an air compressor, and that you use the compressed air to move something, like basically to open or close a valve, something like that. Okay. So pneumatic pressure, pneumatic systems are also used in many machines also. So you don't use it like, you don't open or close a valve like manually or using some mechanical force. You use compressed air for like smooth operation, or so that there is no contact or like, so sorry for the news. Okay. So pneumatic pressure means basically using compressed air, and hydraulic pressure basically means using water pressure to move something inside of an ROV. Okay. Okay. So I'm getting that you already watched the videos. That is why you were able to answer this question. Okay. That this was discussed in the class. Okay. Let's go to the next question. Someone is on unmute. Write down the meaning of these of the following terms. Okay. This was not discussed in this week, but you will be able to answer. It is relevant for every week. In vivo, ex vivo, and third is in vitro. So what are the meaning of these terms? Okay, you can write in the chat box. I will wait for 1 or 2 minutes. This was discussed in week 1. I hope that you already you remember it. In vivo, ex vivo, and in vitro. Can I take the screenshot of the previous page? I will share this presentation with you. You will be able to find it in NPTEL page. Okay, you can take screenshot. Uh, yeah, but I will share. I have shared the last week PPT also. This week PPT will also I will say. So this was the first question. If you want to take a screenshot. And now answer this question. What are the meaning of these terms? Because we are discussing about sensors, in many of the sensors, many of the examples discussed in the class, those are biosensors. So these terms are important so that you know the uh, what is the difference. Okay. Do I have an answer? In vivo means inside body, ex vivo means outside body. Okay. What is in vitro? So the answers are correct, but few differences you have not mentioned. So yes, in vivo is inside the body. Okay. So if you test your sensor like in this manner in vivo, then you will get a very good accurate result, because ultimately you want your sensors to be used on patients and persons, right? But for testing purpose, this is not a good idea. Like people used to do this testing on animals, uh, which is which is kind of cruel. Like uh, it's not appreciated. So how the testing is done normally for different sensors, also for different kinds of drugs, for different kinds of new medicine, nowadays what is done, the experiments are done outside the body. Okay. So that is either ex vivo or in vitro, so both are outside the body. This is also outside the body. What can be an example? Ex vivo, you take outside. Step any answer. Oh, okay, okay. Sorry, sorry. I was on mute. Okay. Thank you for mentioning. Okay. What is in vivo? In vivo means inside the body. Many of you have answered in the chat box. Ex vivo and in vitro both means outside the body. Okay, this is also outside the body. But the difference is what you do in ex vivo. So you perform the experiment. Say you have taken out some cancerous cell and you are doing the experiment. Uh, this is you will do in a lab environment, but with minimal alteration. So this is just like inside the body, but you are just doing it just outside the body, but you are making the environment like same. These are more accurate. You if you cannot you don't have the option to do the testing in vivo environment, you are doing it outside, but you are making the external environment. You are not changing the properties of the cells, you are not changing the environment of the cells, like you are trying to keep it as same as possible as it's inside the body. Okay, that is what ex vivo means. But that is not possible always, so what we go for, so this is, let me write. I'm just writing it. These are not just exact definition. I'm just writing it to understand, and the way I have understood the difference between ex vivo and in vitro. Okay. it is not always possible to do this without changing the environment with the maintaining it the cells, say for example, like exactly same as the cells will be inside the body. So what we go for in vitro analysis. So this is also outside the body. So in vitro means basically the meaning in Latin is in test tube, in glass. Okay, so this means in glass. So these are called as test tube experiment. Okay. So what you do, you normally do it in a test tube. So that is why it is known as like this test tube experiment. Here, the conditions will not be exactly same. The whatever the analyte or the cell you are taking, that will not be exactly same. That is inside the body, but when it is not possible to go for in vivo and ex vivo analysis, then we go for in vitro analysis. Now, why these are relevant? Because to mimic, like when we cannot do the experiment inside the body, what we go for that, we try to mimic those organs or those cells or the system uh, which is inside, which is inside of a person. We try to mimic it using a MEMS system. So those that is why MEMS sensors are basically useful. So you can mimic different organs inside of our body using a MEMS sensor, and that will be used for experiment, different kinds of experiment outside the body. Okay, and few examples were discussed in the lecture videos. One example was patient specific drug testing and the efficiency of drugs or a set of available drugs. Those are tested like in vitro way, or those are tested outside the body use with the help of a microfluidic or a MEMS based sensor or sensor system. I hope this ex vivo and in vitro difference is clear. Okay, I have given you the definition the way I understand it. Yes, study performed in the tissue similar to that of human outside the body. We don't want in ex vivo analysis. And there is not much change of the tissues or the cells. Uh, like it will be similar. The environment or the condition of the cells will be similar as that of like inside of the body. Okay. But to do ex vivo analysis is not always possible. That is why we go for in vitro analysis, which are known as the test tube experiment. So this is the third question. What are the four main components in MEMS system, micro electromechanical system? This was also discussed in the class. So you can tell me the four components in the chat box, and if you want, you can give example of all the four components also. So I'll wait for again a few minutes so that you can write the answer. Or if you want, you can unmute and speak also. Four main components of a MEMS system: microcontroller, micro sensors, micro actuators, and there is one more. Microcontroller is not like exactly correct. It's microelectronics. Yeah, microstructures. microprocessor is that comes under microelectronics. Yes, that is an example of a microelectronic system. uh, can be a part of a MEMS system. Okay. Okay, I think you guys already watched the videos and already know uh, the answer for this question, but I will write the answer. Okay, I will share the slides with everyone. So the four main components are: first one is microelectronics, can be the microprocessors used or the ICs used. The second component is micro sensors. Examples can be pressure sensor, force sensor, etc. Okay, there are many examples, those we will discuss as we go through this course. Then there are micro actuators. Okay, what are different types of micro actuators, micro actuations mechanism we have already discussed at the beginning of this of today's live session. Okay, one example can be MEMS based micro mirrors. Okay, so what mirrors will do, it will control the direction of light. Okay, and these are, so one example I'm just giving you: micro actuator, not the actuation mechanism. The mechanism we have discussed, it can be a thermal expansion or a magnetic like a moving a magnetic part using a magnetic field. So one example can be micro mirrors. Okay, so this to control you can look how micro mirrors are made. I'm also not very sure. I have just seen like a few papers, like and few images how micro mirrors are used in case of optical communication. uh, the fabrication and other mechanism I'm not very sure. uh, but these are like these small components which actually those are used to manipulate certain things. So that is what actuators does. Okay, then the fourth component is microstructures. What can be this microstructure? Say for example, if you are making a lab on a chip, or if you are trying to mimic a like a biological system, then say you have certain microchannels. So those are different structures. Those are not sensors or actuators, or not microelectronics, which is normally the decision making unit. So you need, these are like peripheral or extra units that you need to make the whole MEMS system. Okay, example can be microchannels. Okay, There can be mixtures that mixes the two different chemicals or biological sample. Then there will be sensor that actually senses, and then there will be actuators and other microelectronics component. Okay. Now, if you remember, last week I discussed that basically normally a sensor system, we don't use like sensor individually. We normally make a system out of it. So what we do, we normally have a sensor, then we have a certain decision making unit or signal processing unit, or signal processing unit plus decision making unit, and then actuators. So you will have the, you will send something, you'll take the information, you'll give it to the processor. Okay. That is like the brain, and then based on that some decision will be taken, and that will be given to the actuators, and actuators will perform the work. It's like, say, our nose is a sensor, our brain is the processing unit, and then say our hands and legs are like actuators. So these are the four components of micro electromechanical system. In this week, in this course, we will focus mostly on micro sensors and micro actuators. Okay. Yeah. So I have briefly discussed about the CVT techniques in today. So I will give you one question based on that. Let me write down the question first. What is the primary advantage of using low pressure CVD, which is also known as LPCVD, over atmospheric CVD, pressure CVD? APCVD. See, to maintain a lower pressure compared to LPCVD, you should have you need a pump like vacuum pump to maintain certain level of vacuum. Okay, so that increases the cost of the system. Okay, overall cost of your process, but there are certain advantages of using a low pressure CVD or LPCVD system over APCVD. So what is the main advantage? I'll give you few options. You can think about it and tell me the answer. It's not very difficult to like, you already know the difference between LPCVD and APCVD, so you will be able to answer this way, I think. Higher deposition rates, better film uniformity. You deposit 10 films using CVD, right? So is it better film uniformity? Third option is lower substrate temperature. as I mentioned, we normally do CVD at higher temperature. So, whether the advantage is lower substrate temperature or can it be done at lower temperature, then is use of simpler precursor. Precursors in CVD we don't use like a solid form of target like we use in case of physical vapor deposition. We use certain chemicals, so uh, is the advantage is use of simpler precursor. So think about it and try to give me the answer. If you understand the difference between LPCVD and APCVD, or difference like if you understand the basic of different deposition technique, then you'll be able to answer this question. So how these two are different and what is the primary advantage of LPCVD? Uniform filament, okay. Option B. Option B is better film uniformity. And why do you think that that is the answer? The answer is correct. LPCVD system gives better film uniformity compared to APCVD, but why? Okay, so let me write down the answer. The answer is correct. So the correct option is B, better film quality, better film uniformity. So what happens in CVD? So you normally do it inside a tube, and as I mentioned, this is normally done at very high temperature. So this tube should sustain a very high temperature first of all. So this can be a quartz tube that we normally use in our lab. So what is done here, a substrate is kept here, then the reactant gases are introduced from one side, like in a controlled manner, so there will be MFCs. Now this gas will come and those will decompose into different components, and there will be some reaction will happen at the surface, and after the reaction some byproduct will come, that will result some byproduct, and those will be carried away with a carrier gas. So normally how we introduce these reactants or the precursor, we normally use argon gas, which is a noble gas. It will not react, and that is the carrier gas in case of CVD. So that will so those will flow, so the carrier gas and the reactants will flow, and the chemical reaction will happen, and whatever the byproduct will come from the reaction, chemical reaction, those will be carried away by the carrier gas out from out of the system. Okay, so finally we'll get a substrate with a thin film. Okay. Now, what happens in case of APCVD? So this whole process is done at an elevated temperature, normally at a very high temperature, and at atmospheric pressure. In LPCVD, we connect this tube to a pump to create a like little bit of vacuum, not very high. Okay, so with a vacuum inside the chamber. So that ensures what? So it improves the distribution of the gases, so the gas will flow uh, like in a more uniform way. Okay, that will react with the substrate in a more better way, because there will be like less particle. It's not very high vacuum. It's not like that the tube will be completely particle free. There will be some particle, but number of particles will be very less compared to APCVD, atmospheric pressure CVD. That is why the flow will be very uniform flow of the gases, and that will basically result the better film quality. Now let's check these other options also. Higher deposition rate. So what we normally want, so the ideal condition will be that we want a very good film quality and also very high deposition rate, so that we can grow say very thick films with less amount of time. So you can check what is the growth rate comparison with different kinds of CVD, LPCVD, APCVD. I think it is more for APCVD, not sure. Now lower substrate temperature, as I mentioned that these are normally high temperature, but if we go for other kind of CVD techniques, say PE CVD, then the temperature is typically low. Okay, so this is one advantage of PE CVD, not LP CVD. And use of simpler precursor. So as I mentioned, there are different types of CVD systems available. There is one type of CVD is MOCVD, where some organic precursor, some precursors are used which are normally expensive compared to LPCVD or APCVD system. But in terms of precursor, it's APCVD and LPCVD are similar. So this is not a primary advantage of LPCVD system. So the correct answer is better film quality. I'll write down a line for this just as a justification of this answer. Okay, the reduced pressure allows for more uniform gas distribution and diffusion. There will be less scattering. Yes. How you determine this? How you can say that these films have better uniformity? what you do, you go for some roughness measurement technique. This can be like AFM, atomic force microscopy. If you compare the AFM results of two films, one is grown using LPCVD, one is grown using APCVD system, you will see that the RMS roughness or the mean value of roughness will be different for these two films, and it will be less for LPCVD grown uh, film that is grown using LPCVD system. So how you ensure that it gives better uniformity, you characterize it, and how you characterize is using atomic force microscopy. This is not a part of uh, the content that was discussed in today's in this week, so I'm not going into details, but if you are interested, you can look for different characterization technique that is used to check the film uniformity. Okay, I hope it is clear and there is no question. Pro step coverage, yes. Yeah, what do you mean by step coverage? Okay, see, say suppose you have a film and you have already patterned it like this. This is some substrate, this is some material. Now suppose you want to grow a film like this, uniform film, but it can sometimes your deposition technique may give you film like this, right? This is especially true if it's a very thin film, right? Now you should decide like it's what is the film thickness, what kind of profile you want, whether this kind of profile is acceptable or not, that you have to decide based on your design, based on your requirement. Okay, so that is what means step coverage or step profile. Okay. Okay, I'll write down the next question, question 5. Which of the following statements correctly differentiate between positive and negative photoresist? I discussed about lithography, photolithography, so you can answer this. Photoresist sometimes I will write as PR, so just a abbreviation. First option is positive photoresist becomes insoluble when exposed to UV light. while negative photoresist becomes soluble. Option B is someone is on unmute. Positive photoresist becomes soluble when exposed to UV light, while negative photoresist becomes insoluble. Option C is both positive, I hope that you understand it, it's positive, and negative photoresist become soluble when exposed to UV light. And the last option is it's similar, both positive and negative photoresist become insoluble when exposed to UV light. I will wait for a couple of minutes, you can write down the answer. Option A, positive photoresist become insoluble when exposed to light, and negative photoresist becomes soluble. Is it correct? You can see, I can show you the figure that I mentioned shown you earlier. You can see this is the this is for positive photoresist and this is for negative photoresist. This figure is after development. Okay, UV exposure and development. So if you remember this figure, then you will be able to answer this question. It is very important that you use the right photoresist and right mask, because you can see that this is for positive photoresist, this is the final pattern we got, and this is the negative for the negative photoresist. You can see that this is opposite. If you are not careful with the mask and the photoresist, then you will end up with an opposite image, opposite structure of what you actually wanted to make. Okay. So the question was whether positive photoresist becomes soluble or insoluble in UV light, and whether negative photoresist becomes soluble or insoluble when exposed to UV light? Confused between A and B. So first option is positive photoresist is insoluble, that is option A, and this is soluble. Okay, see, option A is not correct. Correct answer is option B. Okay, that is why I showed you the answer. Answer is option B. So what happens when you expose positive photoresist with UV light? It becomes soluble, it becomes soft. Okay, soluble when exposed to UV light. And negative photoresist becomes insoluble, becomes very hard, actually very difficult to remove negative photoresist after exposure. Okay, UV light. Okay, I will show you the figure. Now you will be able to understand. See, here in this figure, in this portion, let's first consider positive photoresist. Here these portions are exposed, this portion are exposed uh, with UV light. Okay, then what you do, you dip it inside a developer solution. So there will be some developer solution, you will dip your substrate and photoresist, exposed photoresist, inside this developer solution. Now this portion was exposed to light, those will become soluble. See, though these portion get dissolved in the developer solution, and after that you get these patterns. Okay, where light was not exposed, those photoresist will remain. And if it is a negative photoresist, what will happen? uh, when you expose, the exposed portion will become hard. Okay, there will so these photoresist are polymers, so there will be cross linking reaction that will happen due to the exposure of light, and these photoresist will become very hard and will not be soluble in developer solution, where rest of the portion will be dissolved in the developer solution. So wherever light was there, those portion will remain in case of negative photoresist. That means positive photoresist becomes soft or becomes soluble when exposed to light, and negative photoresist will become hard when it is exposed to light. Okay, can give you you can look if you want to see. So there are examples of different positive photoresist and different negative photoresist. So you can search. So and so sorry. Okay, now based on your mask and based on what final design you want, you will use either a positive photoresist or a negative photoresist. Okay, I hope it is clear. So if not, then probably the photolithography part will be discussed in coming videos also. If it is required, if that is not clear, that I can explain you later also in upcoming live sessions as well. So photolithography is something that we do in our lab very frequently. So if you have any question, then I think I will be able to answer your questions. Okay. Yeah. Is it clear? Because for other questions I got the correct answers, but for this question I did not get correct answers. So I hope it is clear. Okay. So let's have another question, question 6. So I'll write down the question. Which of the following, similar question is given in the assignment also, that is why I am taking this. Which of the following equipment is used to kill harmful bacteria in lab? A is autoclave, B is incubator, C is desiccator, is none of the above. So you can tell me the answer. I think many of you already use this, so I'm not sure like whether you are doing your undergraduate or postgraduate or PhD. Many of you, I think you use these equipments in your lab. Okay, so you'll be able to answer this. And also in the lab videos, even if you have not used these, in the lab videos, so though these equipments were introduced, so you can I hope that you have already watched those videos. Okay, so which one of these is used to kill bacteria in lab? A autoclave. Yeah. So yes, the answer is autoclave, option A. So autoclave is like a pressure cooker. So it basically it is also used to for like hydrothermal or solvothermal synthesis, used for some chemical synthesis method also, but it also used to kill harmful bacteria at elevated temperature and pressure. Okay. Uh, yeah. So if you work in a biology lab, then you may have used this. You might have already used an autoclave, and if you work on chemical synthesis of different material, then also you might have used an autoclave. I have used autoclave to make metal oxide semiconductors powders during my master. So this is also used it is also used in synthesis method. And what an incubator, in incubator it is like a control environment where you can control the temperature, humidity and other environmental conditions. If you have some sample or device that needs to be kept in a protected environment, and you keep inside of an incubator. And a desiccator, what is a desiccator? Desiccator means a desiccator is basically when you want to keep your sample in a moisture free environment, so you maintain a slight vacuum and a moisture free environment inside a desiccator. So if you don't have a, like a very controlled environment, or if you don't have a lab where everything is not controlled properly, then you can keep your samples inside a desiccator, so that there is no contamination, there is no change in the properties due to humidity. Okay, so yeah, I think this question is not that difficult, and you have already many of you have already answered this question. So yeah, I think it's already time. If you have any question, I will stop sharing. If you have any question, then you can ask. Otherwise, we can stop the session here. Okay, you are welcome. I hope that the session was useful. Okay, thank you everyone for joining the session, and let's meet in the next week. Okay, same time, and we'll use the same Google Meet link. uh, I, I think few of the assignments are due tomorrow, or I don't remember the due date. Please check those and submit on time. Okay, thank you everyone.